this session, we shall deal with some properties of continuous functions on which some questions are also based. First of all, every constant function is continuous. As in, when you look at a constant function anywhere, you believe that it is continuous and you did not test for it. Well, next one. E bar x, mod x, log 1 plus x, sin x, cos x, etc. are all continuous in their respective domains. No question of any test. One more thing, third property. Every polynomial function is continuous on R. Whatever might be the degree of that polynomial, every polynomial function is continuous on R. And then next one. One of the most beautiful properties of continuous functions is if a function, real function f is continuous on a particular domain, but the domain in the sense, if it is continuous at every point of that domain, then we say that it is continuous on the domain. The domain might be an interval, a closed interval, or open interval, or a set, or whatever you say, an aggregate like that. Well, here, in noting these properties of continuous functions, almost for every property, converse need not be true. What I mean to say is, if you observe a particular function is bounded, then it need not be continuous. First of all, let us recall what do you mean by boundedness. When do you say that a particular function is bounded? It is bounded, function is bounded means its range set is bounded. That is, the set of all f of x's will be lying between two particular real numbers from this to this, that's all. Between these two real numbers only all those f of x's will lie. If you are able to say then that it is a bounded function. Okay, right. What is the essence of this statement? If f is continuous, continuous implies it is bounded. But you see, the converse need not be true. Converse need not be true. For example, consider, that is, we are now going to give a counter example to say that every bounded function need not be continuous. Look here, example, f from R to R Consider the function f from R to R defined by f of x is equal to sin 1 by x for all x not equal to 0. And it is 0 if x is equal to 0. Hence, it has been defined for a very real number. Okay, everybody knows that sin 1 by x, the values of sin 1 by x always lie between -1 and 1. Or otherwise, mod of f of x is always less than or equal to 1. Implies f is bounded, isn't it? The values of sin 1 by x always, whatever might be the value of x, it lies between -1 and 1. So the lower boundary is -1 and the upper boundary is 1. So all the values of f of x will lie between two particular real numbers. Hence we say that f is bounded. F is bounded. Clearly, mod f of x less than or equal to 1, that is minus 1 less than or equal to f of x less than or equal to 1, implies f is bounded. Implies f is bounded. Implies f is bounded. You see, here f is bounded but not continuous at x is equal to 0. Why? Because limit as x tends to 0, sin 1 by x does not exist. That is a famous result. Limit as x tends to 0, sin 1 by x does not exist. That is, it is not continuous at x equal to 0. So, boundedness need not imply continuity, whereas continuity implies boundedness. This is the essence of this statement. Very first property that must be noted in our mind of continuous functions is every continuous function is bounded but not the converse. This is the best example. There are so many other examples also. Observe the signum function, that is f of x is equal to minus 1 if x less than 0, 0 if x is 0, is equal to 1 if x is greater than 0. That is also bounded but not continuous. Like that you can give as many examples as you can. Therefore, continuous implies bounded, but bounded need not imply continuity. The first property. Second property we shall see. If f is continuous at a, g is continuous at consider two real functions f and g which have been defined on the same neighborhood of a, or which have a common domain in every neighborhood of a. Whatever you say, or they have a common domain. That is, both f of a and g of a are defined. More to say, f is continuous at x equal to a, g is continuous at x equal to a. Then number 1, f plus g is continuous at x is equal to a. Number 2, f minus g is continuous at x is equal to a. Number 3, f g is continuous at x is equal to a. Number 4, f by g is continuous at x is equal to a. Provided g of x not equal to 0 or g of a not equal to 0. It is enough to say one thing, g of x not equal to 0, it's enough. Okay, why? Because we are going to have g by g of x in the denominator. We may have to take care of that so that it shouldn't happen 0. It should become 0. Okay, what are the things? This single property, of course the second property, can be named under algebra of continuous functions. F is continuous, g is continuous, then f plus g is continuous. F is continuous, g is continuous, then f minus g is continuous. F g is continuous. F by g is also continuous. Moreover, you can say another thing also. Kf is continuous and x is equal to. For any k belongs to R, of course, k might be positive, k might be positive. Yes, this heading, rather this property gives us 5 simple results regarding algebra of continuous functions. That is, if f and g are individually continuous, then f plus g is continuous, f minus g is continuous, f g is continuous, f by g is continuous. If k is a constant, a real constant, then kf is also continuous. Yes. How can? The proof of this result is very, very simple. But the special thing here is converse of these statements. If you have two functions f and g with you such that f plus g is continuous at x equal to a, then you cannot say that f is continuous here or g is continuous here. that is converse need not be true. The similar is true for f minus g, similar is true for fg, similar is true for f by g and kf also. Yes, let us see. First of all, let us try to give some counter examples to say the converse is not true. As an example, look here. Example. Define f from R to R and g from R to R by f of x is equal to 1 for all x belongs to Q minus 1 for all x belongs to R minus Q. G of x is equal to minus 1 for all x belongs to Q, 1 for all x belongs to R minus Q. The simple example, the simple selection of these two functions f and g give us beautiful counter examples to say the converse of those results need not be true. As an example, look here, f and g, I think you might have recollected, these are of course part and parcel of Dirichlet's function, which is nowhere continuous on R, nowhere continuous. It can never be continuous at any real number. Such a function it is. For that one, I have taken f like this and g like this. You please observe, what is f plus g? F of x plus g of x, 1 plus minus 1, 0, minus 1 plus 1, 0. Therefore, f plus g of x is equal to 0, which is a constant function, always continuous. But neither f nor g is continuous. Therefore, converse of this function need not be true. Converse not true. Well then, fg, consider the product fg. F of x into g of x, what is it? 1 into minus 1, minus 1, minus 1 into 1, minus 1. So, f of x into g of x, that is fg of x is equal to minus 1. Again, it is a constant function, and we know that every constant function is continuous, therefore fg is continuous. But neither f nor g is continuous. Therefore, converse of this theorem, this result is also not true. Moreover, f by g, consider g of x. G of x can never be 0 here. G of x is either minus 1 or plus 1. Therefore, what is saying? This is f by g, 1 by minus 1, minus 1, minus 1 by 1, minus 1. In both the cases, that is, if x belongs to Q, f by g is minus 1. If f belongs to R minus Q, then f by g is minus 1 by 1 minus 1. So, for all x belongs to R, f by g is minus 1, which is a constant function, and we know that every constant function is continuous. Therefore, f by g is continuous, but again neither f is continuous nor g is continuous. Hence, converse of this theorem is also not true. Is also not true. Of course, converse of this might be true by taking k non-zero constant, of course. If kf is continuous, then 1 by mod k into kf is also continuous, therefore f is continuous. Converse for this might become true, whereas converse of these three need not be true. As a whole, only one f minus g is here remain for being explained about the converse. Let us now explain the counterexample for that case also, simply by changing the definition like this. Observe what happens. Simply have taken f is equal to g. F minus g is 1 minus 1, 0 for all x belongs to Q. Minus 1 minus 1 minus 1 is 0 for all x belongs to R minus Q. So, f minus is a constant function, hence continuous, but neither f nor g is continuous. Hence, converse of this theorem is also not true. Converse of that theorem is also not true. Yes. See, now and then we shall be making use of these results as and when such functions appear before us. we notice, we believe, we identify that they are discontinuous. The next property is if f is continuous at x is equal to a, then mod f is also continuous at x equal to a. Mod x is also continuous at x equal to a. Yes, it is also a beautiful result. We know that f of x equal to sin x, f of x equal to sin x is continuous everywhere. Everywhere. Implies mod sin x is also continuous everywhere. Like that, we shall be making use of mod x is continuous everywhere. Okay, mod f of x is continuous everywhere. If is continuous implies mod f is continuous. Here also of special interest is the case to say that converse of this result is also not true. The best example, the so-called Dirichlet's function, come on, bring it to the fray. What happens? F of x is equal to 1 if x belongs to Q, and f of x is equal to minus 1 if x does not belong to Q. You recall and recollect the same function, which is of course called the Dirichlet's function. This is f of x. You see, what is mod f of x? What is mod f of x? Modulus of f of x is modulus of plus or minus 1, that is 1 clearly. Mod f of x is equal to 1 for all x belongs to R, either Q or R minus Q. It is immaterial. Mod f of x is always 1, hence it is continuous at every real number. Why? Because it is a constant function. You see, mod f is continuous, but f is not continuous. Not only like this, you can have as many as you want, as many as you can, number of examples you can have. Signum function, f of x equal to 1 if x is greater than 0, f of x equal to minus 1 if x less than 0, f of x equal to 0 if x less than is equal to 0 is also an example to say that mod f of x is continuous but f is not continuous. Isn't it? As like this, we make use of this property. Next property. If f belongs to C of AB, think you might have recollected the matter about the symbol. It is just nothing but the set of all functions which are defined on closed interrelated to be such that they are continuous on closed interrelated to be. Set of all continuous functions on closed interrelated to be. F belongs to that means f is continuous on that. Isn't it? Continuous on closed interrelated to be. Then it attains its bounds on closed interrelated to be. Here you see, we have two different parts of the sentence to observe. Number one, bounds. What are meant by bounds? Number two, attains its bounds. What do you mean by attaining? Let us try to understand. Like here, it can very well be understood by means of a graph, that is by means of a graphical explanation. Observe the graph. This is the minimum height it could attain and this is the maximum height. What do you mean by height? Y coordinate. What is y coordinate? Y is nothing but f of x, isn't it? That is, this is the least value of the values of f of x. This is the greatest value or supremum, or this is the infimum. Actually speaking, subjectively, those two words infimum and supremum have different definitions, of course. And for the present, for this graph, I think it is not a sin to speak of them like that. Okay, you see, this is the closed interval a to b. The function has been defined on the closed interval a to b. The minimum height is this. Let this be some c. Let this be some k. What can you observe here? The small m is equal to f of c and capital M is equal to f of k, isn't it? Small m and capital M, they are the minimum and the maximum values of f of x in the closed interval a to b. Those two numbers are termed as the bounds of f. We call them bounds of f, and f attains them. What does it mean? They belong to the range of the function. You can write small m, f of something. You can write capital M also, f of something. You can write small m, f of something, capital M also f of something. That is, f attains capital M, f attains small m. What does it mean? F takes the value small m at one particular instance, say small c. And f takes the value capital M at another particular instant, say k. That is, f of c is equal to small m and f of k is equal to capital M. That is the bounds of f. This is the actual meaning of the function, of the property, that f is continuous implies f attains its bounds on closed interval a to b. It is useful at so many other discussions also. Well, next, let us now look at the other property of continuous functions. The next property, this is a very beautiful and important and famous useful property of continuous functions. It is actually installed, rather much research has been done on this concept by Mr. Bolzano. Even though it is a theorem, it is actually a property of continuous functions. What does he like to say, Mr. Bolzano? What is the essence of that? Let us now try to learn. If f belongs to C of closed interval a to b, that is, what I mean to say is f is continuous on the closed interval a to b such that f of a into f of b less than 0, f of a into f of b less than 0, then there exists C belongs to open interval a to b such that f of c is equal to 0. Well, my dear friends, as and when you come across the word there exists C belongs to open interval a to b, then and there itself you understand that the particular statement is a mean value theorem. There exists C belongs to open interval a to b. That is, some discussion has been done about one or more particular points in the open interval a to b. That is the in that way we can smell and spell that the particular statement is a mean value theorem. Okay. How can we remember this? How can we understand this? And how can we use it? Let us now study pictorially. Okay. I am drawing two different graphs on the board. You please observe them carefully. Observe these two graphs very carefully. It is a continuous function. What do you mean by continuity? If you draw the graph for that, there will be no jerks, no breaks, no cuts, no question of any peak points, or no question of any sudden change in the direction like that. It goes on very smoothly. Here, f of a is negative. How do you believe it? Because it is available in the fourth quadrant. And f of b is positive. How can we confirm that? Because it lies in the first quadrant. Well, so this f of x, from negative to positive, it travels without any break. Then one must see and say that that graph should cut x-axis at least one point C. If you name this C, then what is f of c? F of c is equal to 0. Observe the case here. F of a is positive because it is available in the first quadrant. F of b is negative because it is available in the fourth quadrant. So, from positive region to negative region, the graph should travel without any break continuously. And in that journey, it should cut x-axis, no doubt, at say some c. Here also f of c is equal to 0. Like here, f of a is negative, f of b is positive. What do you say about f of a into f of b? In this case, f of a is positive and f of b is negative. Here also f of a into f of b is negative. Now let us try to repeat the statement of the theorem or the property by looking at the graph. If f is a continuous function on closed interval to b, such that f of a into f of b less than 0, then there is at least one c such that f of c is equal to 0. Okay, there is a c or there is at least one c? There is at least one c. You consider this graph. What is f of a? Positive. What is f of b? Negative. How many such c's are here? Three types of points are there at which the function, the graph cuts x-axis. That is, the function vanishes. Who told you that the graph is like this? What can you assure? We can assure that there is only at least one point c such that f of c is equal to 0. This is the essence of the Bolzano's theorem or Bolzano's mean value theorem or the particular character of continuous functions, provided f of a into f of b is less than 0, which has a wide range of applications in the solution of so many transcendental equations also. How are such equations solved? Let us now examine or observe with the help of a particular example. That is the question. First of all, you may not trace from which chapter the question has been given. What type of equation he has given? A cubic equation. X cube minus 3x minus 2 is equal to 0 has at least one real root in. Let us verify. If at all first option is the correct option, let me name f of x is equal to, how to answer this question? Let me write f of x is equal to x cube minus 3x minus 2. What is f of 0? 0, 0, 0 minus 2 less than 0. What is f of 1? 1 minus 3 minus 2. 1 minus 3 minus 2 minus 4 less than 0. Both are of the same sign. Both of them are of the same sign. F of A and f of B negative or positive? Positive. So this option is incorrect. Next, f of 3 you find. What is f of 3? 27 minus 9 minus 2. Minus 9 minus 2 is minus 11. 27 minus 11 is 16. Positive. What do you say about this? F of A and f of B. As in the previous case, or as in the language of the previous property or this Bolzano's theorem, f of A is negative, f of B is positive. So f of A into f of B is negative. Moreover, given function f of x is a polynomial, you see, and we know that every polynomial is continuous. So it is continuous on closed interval 1 to 3, 1 to 3, such that f of A into f of B is less than 0, then surely we'll have a root between 1 and 3. Correct. It is not over. Still there is another option. This is a multiple answer type, we don't know. So we have to test f of 4 also. What is f of 4? 4 cube, 64. 64 minus 14 is 50, positive. So no question of any possibility. Between these two, do you have a root? No. Therefore, what is the correct option? 1, 2, 3. In the open interval 1 to 3, we may have a root of that equation. How that equation has a root? I am naming it some f of x. It is a polynomial, hence it is continuous. Let me name A is equal to 1 and B is equal to 3. F of 1 is negative and f of 3 is positive. F of B is negative or positive. And product is negative. F of A into f of B is negative. By Bolzano's theorem, there is at least one C such that f of C is equal to 0. F of C is equal to 0 means C cube minus 3C minus 2 is equal to 0. Implies C is a root between 1 and 3. Therefore, what is the right option? Open interval 1, 2, 3 is the right option. Like this, we are supposed to have the root of a particular unknown equation. Yes. In this way, we make use of that Bolzano's theorem. Next property. Of course, in very rare cases, that is now and then only, we apply this property. I think it is just enough to understand this picture really. What is he saying? If f belongs to C of closed interval to B, that is if f is continuous on closed interval to B, then f attains every real number between its bounds at least once in open interval to B. What is meant by that? Let us recall the previous graph. There is a graph which has been explained in the previous property. This is a continuous graph, that is a graph of a continuous function. What is the infimum? Rather the minimum value. This is the minimum value. What is the maximum value? This is the maximum value. In between these two, you choose a particular real number, whatever you like between these two. Let me select, say here, let this be some k. Then isn't it? For any real number between the bounds say k, then k is equal to f of something. F attains every real number between its bounds means this. Yes, this is the property. At a particular instant only we use this property.